In this video, we're going to be talking about Chapter 10, Reaction Rates and Chemical Equilibrium. And the topics that we're going to be talking about are defining rates of reaction, and then what exactly is chemical equilibrium and how are these two connected, and then what is an equilibrium constant and how to derive the expression for it, and then use these equilibrium constants to problem solve, and then the effect of changing those equilibrium conditions. So that's based on this principle called as Le Chatelier's principle. And then two more topics that are not present in your textbook, that is an add-on here, is using something called the reaction quotient. That's exactly like the equilibrium constant, but unlike the equilibrium constant, it happens at a time that can either precede or succeed the equilibrium time. And so you use that to predict the direction of a reaction. And then finally, applying equilibrium to slightly soluble compounds, ionic compounds. So you're applying the equilibrium constant to aqueous solutions. All right, so we'll first start with the first part of the topic, 10.1, and that's rates of reaction. So this picture here on the right is indicating what happens over time. So if you look at bananas over a period of days, they rapidly get oxidized. Now, if you look at something like silver, here in this utensil, it gets tarnished, and it takes months for the tarnishing to happen. Or the aging process, which is also a different types of oxidative process, takes years. So basically, rate is measuring something, measuring a change that is happening over a period of time, and the time can be in days. In terms of reactions, it'll happen in minutes or hours, whereas other things happen over a longer period of time. All right, for the reaction to occur, there has to be one of the conditions is that those reactants have to collide. They have to bump against each other. So you can see nitrogen and oxygen are components of air. And most of the time, of course, gases are unreactive. They just bounce harmlessly off each other even when they collide. The collisions are elastic. But once in a while, some of the nitrogen and oxygen molecules, they have enough energy from that collision to react and form a product, such as nitric oxide, nitrogen oxide. Um, so, when is that collision successful? So that collision is successful if the energy of that collision is enough to transform these reactants into products, all right? If it is, they collide, but the energy is insufficient for them to become products, then they just bounce off each other. So that's most of the time. It's just elastic collisions. They don't lose much energy or gain energy or anything of that sort. Energy remains a constant. But occasionally there is enough energy to transform them into products. Another condition is that they have to be oriented properly. The reactant molecules have to be oriented properly. The wrong orientation will not lead to product formation, all right? So the correct orientation will then lead to the product formation. So as you can see here, both of them, both nitrogen and oxygen, are in the wrong orientation, and so they just harmlessly bounce off each other. Same thing over here. But when they are in the correct orientation, then with the correct amount of energy, then products are being formed. So those conditions required for a successful reaction are collision, orientation and energy. All right, okay. So the first conditions is they have to bump into each other. The second is that they have to be oriented properly. And then the third is they have to have enough energy from that collision to overcome a barrier, an energy barrier, and get transformed to products. So that energy barrier is called as the activation energy. All right, so you see nitrogen and oxygen here, and if you look at the energy levels, you can see that it's steadily rising. So there is an energy requirement that they have to overcome to get to the other side and become products. All right, okay. So why do reactants climb the hill? To get to the other side and become products. All right, so that hill that they're climbing is called as the activation energy. This is the minimum energy required for the reactant bonds to break and new bonds, the product bonds, to be formed. Okay, so a rate of reaction is basically the change in something, right? So the change over a period of time. So the change in concentration of the reactant, all right? So the reactant concentration is disappearing, or the product concentration is appearing or increasing over a period of time. This is very similar to measuring speed, all right? You might be driving anywhere, whether it's a freeway or driving anywhere. So that's basically the speed, which is also rate, is the distance covered in a unit of time, whether it's 70 miles per hour, all right, where the mileage is the numerator, the hour is the denominator, and so on. So here we are measuring concentration, all right, like molarity, over a period of time. So if the activation, that energy barrier, is low, then of course it's very easy for the reactants to become products. But if that energy barrier, that hill that they have to overcome, is too high, then the reaction rate is going to be very slow. So this rate to get to the other side is affected by temperature, because temperature, if you increase the temperature by at least 10 degrees above what is the normal temperature, what happens is the rate tends to double for every 10 degrees rise in temperature, because now those reactants have enough energy from the heat to get to the other side and become products. All right. If you have more reactants, right, per density in a given area, there's more reactants, so there's more collisions. All right, so reaction concentration will lead to more collisions, and more of those collisions will then become more successful and become products. Adding a catalyst is basically lowering the activation energy so that more of those reactants can become products. All right, so if you increase the temperature for every 10 degrees centigrade, the rates are doubling. That means the reactants move faster, they collide with more energy. More energy collisions can then be successful, leading to products. All right, so if you have just a couple of reactants, then maybe one collision, so not much products. If you have more reactants, then you can see the possible number of collisions can increase that much more. All right, four of each type of reactant can lead to at least four possible collisions, and therefore more products can form. Okay. Activation energy, once it's lowered using a catalyst, means you can get to the other side a lot faster and with a lot more of the stuff. All right, so most of those collisions, remember, are unsuccessful because they can't cross that energy barrier. But if you lower it, more can get to the other side. Okay, so increasing temperature means more collisions, and more collisions mean that it can lead to collisions that are successful because they have enough energy to cross the activation energy barrier. Increasing reactant concentration therefore can also lead to more collisions because there's more reactants per density in a small area, and therefore it can also lead to more successful collisions. Adding a catalyst will just lower that energy barrier so that more of the reactants can become products. So indicate the effect of each factor listed on the rate of the reaction, all right, whether it's increasing, decreasing, or no change. So raising the temperature of this reaction should increase the rate, okay. Removing oxygen, so you're decreasing reactants. Remember, increasing reactants can lead to more products, all right, so it would be D, decreases. Adding a catalyst will mean that you increase the rate, right? Lowering the temperature, that won't help, because then the reactants are going to become sluggish, they won't move as fast, and so it would decrease. So this would be I, this would be this would be D, this would be I, and this would be D. State the effect of each on the rate of reaction, as it increases, decreases, or no change. Decreasing the temperature, which would mean that decreasing the rate. Removing the reactants would also mean decreasing the rate. Adding a catalyst would increase the rate. Placing the reaction flask in ice, again lowering the temperature, decreased rate. Increasing the concentration of one of the reactants would also increase the rate. So, in cars, we have something called as catalytic converters. All right, so catalysts are used in the car engines, and the reason is that as the gasoline, the octane, which is the major component of gasoline, burns, it forms byproducts like carbon monoxide and nitrogen oxide, or nitric oxide. All right, so it's burning in the presence of oxygen from air, and these are some of the byproducts. These are very harmful, and therefore instead of releasing it into the atmosphere, they are converted first into harmless products such as carbon dioxide, or broken down into like nitrogen, oxygen, and then released back into the atmosphere. All right, so that is done with the help of catalysts such as platinum or palladium. These are called as catalytic converters. They're just powdered metals. They have a large surface area on which these gases can come and anchor. So once you have a surface on which the gas can latch on, it's easy then to break up this gas like nitric oxide into oxygen and nitrogen, which then come off through the tailpipe into the atmosphere. Or carbon monoxide can then be broken down with the help of oxygen, and formed into carbon dioxide, which also then comes off into the atmosphere, and it's perfectly harmless. All right, we'll stop here and continue this next section in the next video.